Moving forward with the MJOs, I mentioned waves already. So we can start by looking at the wave number frequency diagram for the OLR. Here it is the cloud top temperature actually from July 1983 to June 2005, summed from 15 north to 15 south, which tends to be the meridional region band in which MJOs propagate. So they are plotted as the ratio between the TB power and power in a smooth red noise background. It's a way of doing things. Let's see, we have here n equals first mode equatorial Rossby waves for different equivalent depths. If you don't know what an equivalent depth is, you can again go back to the podcast in my tropical dynamics course, but think of it as a way to create a parameter that is useful for describing waves in a rotating framework where stratification is a factor. So you try to create an equivalent depth over which you create a homogeneous fluid by using some approximations, and that allows you to write wave number dispersion relations. So you can see that when you change the equivalent depth, the waves frequency and speed wave number change. So obviously you know how to do the phase speed and the group speed and so on. So equatorial Rossby waves propagate westward at shorter wave smaller wave numbers, and at longer wave numbers, shorter wavelengths, they become eastward. But nonetheless, there is the westward propagating inertial gravity wave, and here are the Kelvin waves for various equivalent depths. But there is the MJO. Okay, so there are lots of ways to explain why MJO is not fitting into these free waves that we can get from shallow water equations. That is done typically in tropical dynamics by simplifying the equations, linearizing, looking for wave solutions, and so on. And there are also processes that have to be explained in terms of why MJOs project onto these Rossby and Kelvin waves, but they propagate slower than these free waves. You can think of these as basically free waves, and these are waves that we will come back to later on, called convectively coupled equatorial waves, which is used as a way to say why they move more slowly than free waves and so on. Okay, so that diagram is something you should remember if you can. Kelvin waves here, gravity waves, equatorial Rossby waves, and then inertial gravity waves eastward and westward propagating. The MJO needs an index, especially for identifying it, tracking it, and of course forecasting it. And one of the more popular indices is the so-called real-time multivariate MJO index, referred to as the RMM index. And not everybody agrees as this is the best one. There is also OLR based index and so on. Nonetheless, we will see more of this as we go along. This is showing the spatial structures of the EOF 1 and 2 of the combined analysis of OLR, which is outgoing long wave radiation, as you probably know already, and the vertical shear, so 850 hectopascal and 200 hectopascal zonal winds. As each field is normalized by its global variance before EOF analysis, its magnitude may be plotted on the same relative axis. Multiplying each normalized magnitude by its global variance gives the field anomaly that occurs for a one standard deviation perturbation of the principal component, as given for the absolute maxima of each field. There's a lot of processing involved, so you take the total signal, you bandpass filter it, you remove the harmonics, the seasonal cycle, and then some sort of annual cycle, and so on. The variance explained after doing all this by the EOFs is 12.8% and 12.2%, which is typical for when you do combined EOFs. Okay, individual EOFs tend to give high explained variances, but this is explained variance of what remains after you've done all the filtering and subtracting the annual cycle and so on. So you have to be careful about what is the percentage of the total variance that is explained by doing this. That can be very small. Okay, normalized magnitude is shown here. So we are looking at OLR. So when OLR is negative, obviously it's in a convective phase, so minus 8.5 watts per meter squared here. And when it's so you can see there is a convective phase here in the maritime continent region, and ahead of it in the central western Pacific there is all the way into the Atlantic there is a dry phase, and then you have corresponding upper level winds. They are easterly here and westerly. Let me make sure. So this is the 200 hectopascal, that is 850. So there is we know that there is convergence into the convective phase, so you have westerlies behind it and easterlies ahead of it, and opposite phase in the upper level with easterlies and westerlies, so you know what you expect. And this is the second mode. So this is showing OLR positive here and negative over here. So it's typically the way EOFs are constructed, they are orthogonal to each other. And you have again winds that correspond to that. So you have essentially a way to explain the strength and the speed of propagation using these RMM1 and RMM2, and they are projected into this phase space here, with phase 1 being in the western hemisphere and Africa, phase 2 being in the western Indian Ocean, eastern Indian Ocean, phase 4 is getting into the maritime continent, phase 5 transitioning into the West Pacific, 7 and 8 into the East Pacific and back into the western hemisphere. So what is shown here are various events: October, November, December, January, February, and March. So these are examples of RMM phase diagrams for October 1, 2003 to March 31st, 2004. The colored circles are plotted every 7 days from October 1. Days inside the unit circle are considered to have weak MJO activity. So you can see that they are all going counterclockwise. So you are going from the western hemisphere or western Indian Ocean towards the maritime continent, western Pacific and back. So you are going in this direction, and you can see that the MJOs can start anywhere. This one is starting here in October in the eastern Indian Ocean, and then stumbling out of it into the maritime continent and then back. Whereas there are others, I don't know, pick another one. This one is just wandering around here, weak, doesn't do much, so doesn't have a good structure, which can imply predictability limitations as well. There is a strong one here in March, which is seems to be starting here and has some confusion before it goes out and evolves systematically into the Pacific and then disappears. So basically that means even though we are always talking about them being born in the western Indian Ocean and propagating eastward across the maritime continent into the western Pacific and eastern Pacific and so on, it's not always the case that they are all so systematic. So that can also mean that when you filter the data and project them onto this RMM index, you may be capturing other signals, you may be aliasing some other features into the MJOs, but one has to be careful about those anyways. There are ways to do diagnostics to make sure that indeed you are capturing an MJO and not something else. What else can I say? Let's stop here and come back and look at the observed MJO structure in the next podcast. So RMM index is square root of RMM1 squared plus RMM2 squared, where RMM1 and 2 are these EOFs of OLR 850 hectopascal winds, 200 hectopascal winds. Okay, this is the most commonly used MJO index to track MJOs and to track forecasts, forecast skills, etc.